Okay, so today we're going to look at something called L'Hopital's rule. That's as close as I can get to the French pronunciation. Um, I have a friend who used to teach math and French, which is an interesting kind of thing. And I asked her how to say it once, and she said it, and I tried to do it, and she gave up after a while. So, anyway, um, this has to do with doing limits, which was what we did at the very beginning of the year. So earlier, we used algebraic methods to find limits of the indeterminate form 0 over 0. So we would do things like this. If you had the limit as x approaches 2 of x squared minus 4 over x squared minus 2, if you just substitute in 2, you get 4 minus 4 is 0 in the numerator, and 2 minus 2, which is 0 in the denominator. And 0 over 0 doesn't have any meaning at all. The problem is that 0 in the numerator typically means that the fraction will be 0, right? 0 in the denominator means the fraction is undefined. And this limit actually is defined. So what we would do is we would go, okay, we can factor that. So we would do the limit as x approaches 2, and we would factor the numerator to x plus 2 times x minus 2 over x minus 2. And although at 2, x minus 2 over x minus 2 is 0 over 0, any place other than 2, x minus 2 over x minus 2 is going to be 1, right? For any x value. Remember that a limit, we care what happens near this value, not at this value per se, right? So we could go, okay, well, this is 1 everywhere except for at 2, so we would cross that out and say that's 1, and then this limit is 4. And if you were to graph x squared minus 4 over x minus 2, there would be a hole in the graph at x equals 2, but the y value would be very close to 4. Okay, we also did ones like this, where we had the limit as x approaches 5 of the square root of x minus 5 over x minus 5. Again, you get 0 in the numerator and 0 in the denominator if you try to substitute in directly. And what we ended up doing on this one, you may not remember, this is a little bit different. We multiplied top and bottom by the conjugate of the square root part. That is, we multiply by the square root of x plus the square root of 5 over the square root of x plus the square root of 5. So in the numerator, what that had the effect of doing is we have the limit as x goes to 5, the square root of x plus the square root of 5 times the square root of x minus the square root of 5. If we were to multiply all that out, we would get x minus 5. The reason why is you'd have the square root of x times the square root of x is x, negative square root of 5 times positive square root of 5 is negative 5, and then your middle terms, you would have a negative square root of 5 times the square root of x and a positive square root of 5 times the square root of x. Those would drop out. In the denominator, we did not multiply all that out. We want it to be in factored form. So it's x minus 5 times the square root of x plus the square root of 5. And the same sort of thing happened that happened on the last one. Any place other than 5, x minus 5 over x minus 5 is equal to 1. And now we can just let x go to 5. We have 1 over the square root of 5 plus the square root of 5, so that's 1 over 2 square roots of 5. The problem that we had with this, if you remember, is that you kind of had to go, okay, on this type I have to do this thing, and on that type I have to do that thing. So today we're going to learn something called L'Hopital's rule, which is a way to handle problems like this where we can handle all of them kind of the same way. So consider for a second, if we have the limit as x goes to a of f of x over g of x, where f and g are defined in an open interval about a. Okay, so these two functions have to be defined around a to both sides. If the limit as x approaches a of f of x is 0 and the limit as x approaches a of g of x is 0, then the limit as x approaches a of f of x over g of x is an indeterminate form of the type 0 over 0. There's more than one type of indeterminate form, and we'll talk more about that. So how can we deal with this? Well, after we had done limits, we learned about derivatives and we learned about tangent lines. So the tangent lines for f and g at x equals a are indistinguishable from the graph of f and g near x equals a, right? When we zoomed in on the tangent line, you couldn't tell the tangent line from the function. So what we're going to do is we're going to replace f and g with a tangent line approximation. So the limit as x approaches a of f of x over g of x is going to be the limit as x approaches a of f of x plus f prime of x times x minus a, right? That's the tangent line approximation. And then the same for the denominator. And since f of x and g of x are both approaching 0, I can drop those. And I'll have f prime of x times x minus a over g prime of x times x minus a. And then the x minus a's will cancel each other out, because everywhere other than at a, x minus a over x minus a is equal to 1. So we end up with just the derivative of f over the derivative of g. So what we can do is the limit as x approaches 2 of x squared minus 4 over x minus 2, which is the one we did previously. Since both the numerator and the denominator go to 0, we simply take the derivative of both, 2x and 1, and evaluate it as x approaches 2, and we get exactly the same answer without having to do, any algebra to it. So this is the idea behind L'Hopital's rule. If you'll turn to the back, here's what L'Hopital's rule says. If f and g are functions that are differentiable in an open interval containing a, except possibly at a itself, it's okay if they're not defined at a, because remember, with limits, we don't care what happens at the point, we just care what happens near that x value. So then if the limit as x approaches a of f of x over g of x produces the indeterminate form 0 over 0, or plus or minus infinity over plus or minus infinity, then the limit as x approaches a of f of x over g of x is going to be the limit as x approaches a of f prime of x over g prime of x. All right, so let's look at some example problems. For these, the first thing that you want to do is establish that the numerator and the denominator, independently of one another, go to either 0 or infinity. So I'm going to do that over here. I'm going to say, all right, so the limit as x approaches 0 of e to the 2x minus 1, as x approaches 0, 2x will be 0, e to the 0 power is 1, so that's 1 minus 1 is 0. And the limit as x approaches 0 of x, well, it just told me x is approaching 0, so x is approaching 0. So we have to establish that first, and it has to be independently. One of the things that'll get you absolutely reamed on the AP exam on a free response question, don't write this, is if you write that. If you write that's equal to 0 over 0, points will be deducted, no questions asked. Because you're saying that this limit equals something that doesn't make any sense. So don't ever write that. So now we'll just take the derivative of the numerator and the denominator independently of one another, so we're not using the quotient rule. So the derivative of e to the 2x will be e to the 2x times 2, because of the chain rule. And the derivative of the negative 1 is 0, so that just goes away. The derivative of x is just 1. At this point, I know I'm not going to be able to use L'Hopital's rule a second time. Sometimes we will use it a second time because the denominator is going to go to 1 as x goes to 0. So, as x goes to 0, e to the 2x goes to 1 times 2 is 2. That quotient goes to 2 as x goes to 0. For this next one, you'll see that sometimes we will have to use L'Hopital's rule more than once. I usually do it when I'm checking, I usually do it in my head real quick first before I write out the numerator and denominator separately. But cosine of 0 is 1, minus 1 is 0, 0 squared is 0, so okay. I know I'm going to be using L'Hopital's rule because both the numerator and the denominator go to 0. So we'll apply L'Hopital's rule by taking the derivative of the numerator and the denominator. So the derivative of cosine of 3x is going to be negative sine of 3x times 3 because of the chain rule, and the derivative of the negative 1 is 0, all over 2x. Well, now I have a different problem. If I substitute in, sine of 0 is 0, so the numerator is 0, and 2x will be 0 as x goes to 0. So I'm simply going to apply L'Hopital's rule again. To do that, I have to justify that I can, and I'm going to rewrite the numerator as negative 3 sine 3x. That goes to 0. And the limit as x goes to 0 of 2x is also 0. So now, taking the derivative of the numerator and the denominator independently of one another, I'm going to have negative 3 times the derivative of sine is cosine of 3x. I have to use the chain rule again, so times 3 all over 2. Again, I noticed that the denominator is not going to go to 0 as x goes to infinity. Once either one of them isn't going to 0 anymore, you know you're not going to be able to use L'Hopital's rule again. So the denominator goes to 2. The numerator, as x goes to 0, 3x goes to 0, cosine of 0 is 1, and negative 3 times 1 is negative 9. This goes to negative 4.5. Which is sort of a surprising thing. All right, let's take a look at this next one. As x goes to infinity, both the numerator and the denominator clearly go to infinity, right? That said, I could spend a very long time using L'Hopital's rule over and over and over and over again, right? For a problem like this, I don't use L'Hopital's rule. You would have to use it, 6 times before you got to anything useful. And to me, that's just way too much. What I remember is something called dominant terms. So as x goes to infinity, which term in the numerator has the greatest impact on the value of the numerator? X to the 6th. And in the denominator, what of these terms has the greatest effect on the value of the denominator? Yeah. So I'm just going to go, okay, this is going to be the limit as x goes to infinity of x to the 6th over x to the 8th. And I will simplify that to the limit as x goes to infinity of 1 over x squared. As the denominator of a function gets large without bound, and you have a finite numerator, what does this go towards? 0. So that's the dominant terms idea is especially useful when you have polynomials top and bottom. And you probably did some of that in pre-cal. All right, and then this last one, limit as x goes to infinity of x over the natural log of x squared. Clearly I can't use the idea of dominant terms here. As x goes to infinity, both of these are going to go to infinity, so I'll write that out. The limit as x goes to infinity of x is obviously infinite. And the limit as x goes to infinity of the natural log of x squared is also infinite. Right? Natural logarithm is a very slow growing but still growing function all the time. So we'll take the derivative numerator and denominator. So I'll have the limit as x goes to infinity of the numerator, I'll have 1. Here, the derivative of natural log of x squared is 1 over x squared times the derivative of x squared, which is 2x. I'm going to clear out the complex fraction. You can think of it as multiplying top and bottom by x squared, or you can just think 1 over x squared is x squared. So that would be the limit as x approaches infinity of x squared over 2x. Now that they're both polynomials, we can go, okay, and they're actually monomials, they only have one term, I can cancel out an x and have the limit as x goes to infinity of x over 2. Here the numerator is going to infinity and the denominator is a finite constant, so this goes to infinity. And if you think about this for just a second, if we're looking at y equals x, it looks like this, right? And the natural log of x squared, well, it's going to grow a little bit faster than natural log does, but it's still doing this, right? As x gets really big, the distance between these keeps getting bigger and bigger and bigger. So it makes sense that this limit approaches infinity. Okay, any questions about that?